Somewhere out there, 4 light years from where you're sitting right now, there is a star. We've known about it for centuries. We've dreamed about it for decades. And if you left for it today, in our fastest, most advanced spacecraft ever built by human hands, you would not arrive in your lifetime. You would not arrive in your children's lifetime. 81,000 years. That's how long the journey would take. Long enough for an entire species to rise and fall and be forgotten before the ship even slowed down to arrive. Which raises a question that should terrify you a little. If we are a species that put footprints on the moon, that flew machines past Pluto, that builds rockets powerful enough to tear themselves apart, why can't we cross a gap that, on a cosmic map, barely qualifies as next door? The answer is the same one that has haunted every engineer who has ever tried to leave this planet. We have never actually solved the problem of distance. We have only ever found new ways to delay defeat by it. Tonight, we go looking for the machine that finally beats it. Auburn, Massachusetts. A cold morning, almost a century ago. A man named Robert Goddard is about to light a fire that will eventually carry human beings off this planet. He has no idea how far this fire will eventually travel. He just wants to know if it will fly at all. It rises 12 meters. 12 meters is nothing. You could throw a rock higher. But 12 meters, on that day, in that field, is the difference between fantasy and physics. This is the moment the chemical rocket is born, and for the next 100 years, it will be the only way humanity knows how to leave home. The idea, underneath all that fire, is almost embarrassingly simple. Take a fuel. Take an oxygen source. Mix them. Light them. Hot gas wants to expand violently in every direction. Point that explosion downward, and Newton makes you a promise. Every action has an equal and opposite reaction. Push the fire down. The sky pulls you up. It's violent. It's loud. It's worked over 7,000 times since the first satellite reached orbit in 1957. But it is hiding a secret. A flaw baked into the very fire that makes it work. Look closely at a Falcon 9 rocket standing on the pad, fully loaded. It weighs over 500,000 kilograms. Almost 400,000 kilograms of that is fuel. That leaves almost no room for the thing the rocket was actually built to carry. Astronauts call this the tyranny of the rocket equation. Every gram of fuel you carry needs more fuel just to lift itself. And there is a number that explains exactly why this tyranny exists. Engineers call it specific impulse. Think of it as a rocket's fuel economy, how much push you squeeze from every drop you burn. A chemical rocket is a supercar with a 1-mile range. It can scream off the line faster than almost anything we've ever built. And then it's out of gas. Stranded. Drifting. Which is fine if your trip is 8 minutes to orbit. It is not fine if your destination is a planet that takes months to reach. And it is most certainly not fine if your destination is a star. So somewhere, decades ago, a different kind of engineer asked a dangerous question. What if we stopped burning fuel and started saving it instead? This is NASA's Dawn spacecraft, somewhere out past Mars, heading for the asteroid belt. It is not on fire. There is no explosion behind it. There is no roar at all. Just a quiet, glowing whisper of blue light. This is an ion thruster. And it is, in its own strange way, one of the most efficient machines humanity has ever built. Instead of igniting fuel, it grips individual atoms, usually xenon, sometimes krypton, inside invisible electric and magnetic fields, and flings them backward at speeds you cannot fathom. 140,000 kilometers per hour. For a single atom. Throw something away fast enough, and Newton's law still applies. The ship creeps forward. Fly one of these for 10 times longer than a chemical rocket, and you'll go 10 times farther on the same fuel. It sounds like the answer. It sounds like we solved it. Until you ask one more question. How hard does it actually push? The honest answer is almost cruel. About as much force as a piece of paper resting on your hand. That is the thrust of an ion engine, the full, maximum, straining output of one of humanity's most advanced propulsion systems. It can take days of continuous firing just to nudge a spacecraft up to 90 kilometers per hour, slower than a car on a highway. Eventually, given enough patience, it can reach extraordinary speeds. NASA has imagined missions where it pushes a craft past 300,000 kilometers an hour. But there is a catch buried inside that patience. If anything resists it, gravity, friction, drag, it simply will not move. You could never launch a rocket off the ground with one of these. It would just sit there, humming, useless. And so humanity finds itself holding two engines, and neither one is enough. One is a sprinter that runs out of breath in minutes. The other is a marathon runner that can barely climb out of bed. And somewhere between those two extremes lies every dream we've ever had about leaving this solar system. So what happens when neither sprinting nor patience is enough? NASA wants human beings standing on Mars within the next decade. Not robots, not rovers, people. And that single goal exposes the wall both of our existing engines slam into. You don't just need an astronaut, you need their air, their water, their machinery, their shelter, spare parts, years of supplies, mass, enormous, unforgiving mass. Chemical rockets choke on mass like that. They're already drowning in their own fuel before the cargo is even loaded. And ion engines, with their gentle, paperweight push, would take years just to get that much mass moving at all. There is, perhaps, one elegant escape from this entire fight. One idea that doesn't try to outmuscle gravity at all. A Japanese construction company believes that, instead of fighting gravity with fire, we could simply climb past it. A single cable, anchored to a counterweight in perfect geostationary orbit, stretching all the way down to solid ground. No explosion, no fire, just a climb. The company calls for a cable 96,000 kilometers long, woven from carbon nanotube, anchored to a counterweight heavier than the Eiffel Tower 1,000 times over. Work could begin within the decade. The climb to a finished elevator could take another 20 years after that. If it succeeds, by the middle of this century, climbers carrying 100 tons apiece could ride into orbit on nothing but a cable and patience. It is beautiful, it is audacious, and it still only solves half the problem. Because an elevator can lift you off the Earth, it cannot carry you to Mars or to a star. For that, we still need an engine. And so NASA went looking somewhere far more dangerous than carbon nanotube. They went looking inside the atom itself. There is a kind of fire more powerful than anything humanity has ever lit on purpose. And for decades, it has terrified the very engineers who dream of using it to fly. NASA calls it nuclear thermal propulsion. The principle is almost frighteningly elegant. Use a nuclear reaction to superheat a flowing propellant. Let it explode outward into space, far hotter and faster than any chemical reaction could ever manage. Twice the efficiency of a chemical rocket. Twice the punch from the same tank of fuel. There's a second version too. Instead of heating propellant directly, use the reactor to generate electricity and feed that power into engines that work like the ion thrusters we already met. Suddenly, those gentle, paperweight engines aren't gentle anymore. They have a power plant behind them. NASA believes this single shift could cut the journey to Mars almost in half. But this technology has a ghost buried in its history, and the ghost is terrifying. In the 1960s, NASA seriously considered a design called Project Orion. The plan: detonate small nuclear bombs, one after another, directly behind the spacecraft and simply ride the shockwaves into space. A spacecraft powered by nuclear warfare against itself. It was, perhaps mercifully, abandoned. Today's nuclear rockets are far more disciplined. They wouldn't launch from Earth's surface at all. They'd be assembled and ignited only once safely in orbit. Up there, even the worst-case scenario, a reactor meltdown, threatens no innocent bystander on the ground, only the crew aboard, which is, somehow, meant to be reassuring. Because radiation was already going to be the silent enemy of any Mars mission, nuclear engine or not. A single 6-month trip to Mars could expose an astronaut to more than half of the radiation they're allowed to absorb across their entire career. And some mission plans don't call for 6 months. They call for 2 to 3 years, round trip. Every extra day in space is another day closer to a limit no one wants to cross. Which is exactly why a faster nuclear engine is so tempting. Less time exposed, less time vulnerable. But faster nuclear engines carry their own quiet poison. The very propellant that gets superheated and blasted backward becomes irradiated in the process. Fire that engine too close to a planet's atmosphere, and you are not just leaving a trail. You are leaving a wound. So even here, even with the raw power of the atom itself, there is no purely clean victory. Only trade-offs, carefully managed. And nuclear power, for all its strength, still cannot answer the question that started this entire search. How do you cross a distance measured not in months, but in tens of thousands of years? For that, NASA went looking for an engine that needed almost nothing at all. In 2024, NASA launched something almost absurdly simple: a sail. 9 meters by 9 meters of reflective material unfolded by arms stretching 7 meters into the void. It carries no fuel, no engine, no combustion of any kind. Just a simple, almost poetic fact of physics. Light itself carries momentum. Every photon that strikes that sail gives it the faintest possible push. One photon is nothing. But the sun never stops sending more. It isn't a flawless triumph. One of its arms bent slightly during deployment, and the little sail now tumbles slowly as it circles the Earth. But even tumbling, it's teaching engineers something invaluable. Because future sails are imagined far larger than this one. Sails the size of a basketball court and beyond. For missions with no human passengers and modest budgets, sailing on starlight may be the cheapest way to cross the solar system there is. But there's a stranger cousin to this idea. One that doesn't even need a physical sail. Charge a set of wires with electricity and they create an invisible field, a sail made of nothing but repelling charge. Solar radiation pushes against it just the same. Not through reflection this time, through repulsion. One company has already tested this idea, using the very same field, in reverse, as an invisible brake to pull dying satellites back down out of orbit. A field of light, pressure, and electric charge, doing the job an engine used to do. And in 2024, NASA went one step further, exploring something almost nobody expects. A simple wire, trailing behind a spacecraft, can push directly against a planet's own magnetic field. Run the right current through it, and that invisible push can actually raise a satellite's orbit. No fuel burned, no propellant spent, just electricity harvested from sunlight and a length of wire. For a satellite, that means years of extra life. For humanity, it means proof that movement through space doesn't always require burning anything at all. These ideas are gentle, elegant, almost free. But gentle has a limit, and that limit has a name. Sunlight only works as long as there's a sun nearby to provide it. And the moment you leave this solar system behind, there is no sunlight left to sail on at all. This is interstellar space, not a metaphor, not poetic exaggeration, just nothing, for trillions upon trillions of empty kilometers. The nearest star beyond our own sun is called Proxima Centauri, 4.25 light years away. On a galactic map, it's practically our next-door neighbor, and it might as well be on the other side of the universe. In 1998, an ion-powered probe called Deep Space One reached a speed of 56,000 kilometers per hour. At the time, it was a triumph, a milestone. At that speed, the journey to Proxima Centauri would take 81,000 years. 81,000 years ago, no human being had ever drawn a picture, planted a crop, or built a permanent home. That is how far back you would have to travel in time to find the moment that matches how long this single one-way trip would take. No human being, no matter how determined, no matter how brave, is built to survive that kind of waiting. So either we accept that the stars are simply not for us, or somewhere, someone has to imagine something humanity has never built before. In 2021, a NASA scientist claimed he might have found exactly that. And for a few electric weeks, the entire world believed faster-than-light travel had just stepped out of science fiction. The claim was almost too good to be true. A real warp bubble. Microscopic, humble, but real. The idea behind it is one of the strangest loopholes in all of physics. Nothing can travel through space faster than light. Einstein was clear about that. But there is no law that says space itself can move faster than light. Gravity already does this, in its own quiet way, bending and contracting the space around massive objects. So what if you could engineer that effect on purpose? Contract space ahead of you. expanded behind you. You wouldn't be moving through space at all. You'd be riding inside a bubble while space itself does the moving for you. It's like outrunning a speed limit, not by breaking it, but by moving the road. There's just one problem. A problem so large it borders on impossible. To stretch a space like that, you would need a form of matter that pushes instead of pulls. Negative matter, the opposite of gravity itself. We have never observed it. We are not even certain it can exist. And some models suggest the energy required would exceed every joule of positive energy that exists anywhere in the observable universe, which is exactly why the 2021 claim felt so electric. A microscopic bubble would have been the first real proof that any of this could ever work. But as other physicists studied the work more closely, the bubble began to disappear. It hadn't actually been built. It hadn't even been observed. The scientists had been studying something entirely different, a quirk of quantum physics that, under a very particular squint, resembled the math of a warp bubble, a shadow on the wall, mistaken, for one breathless moment, for the real thing standing behind it. The dream did not die, but it retreated back into the realm of theory, waiting for physics itself to catch up to imagination. So if warp drives remain, for now, a story we tell ourselves, what is left? One idea. Stranger than fire, stranger than the atom. But, unlike the warp bubble, built from physics we have already proven works. What if the sun didn't have to travel with you at all? What if you simply built your own? Picture an enormous laser array, built here on Earth or floating in its orbit. Instead of carrying fuel with you, into the emptiest, darkest reaches of space, you let the energy come to you. A beam of photons, or a stream of electrons accelerated to nearly the speed of light, constantly chasing the ship, constantly feeding it power, an electric thruster that never runs out of electricity, because the electricity is being beamed to it every second, all the way from home. In 2024, two researchers ran the numbers on exactly this idea and published their findings in a leading astronautics journal. A probe roughly the size of Voyager, pushed by a beam of accelerated electrons, could reach 10% of the speed of light. Remember the number that opened this story. 81,000 years to reach the nearest star. At 10% the speed of light, that number collapses. 40 years. Not 81,000, 40. A single human lifetime. A journey a person could begin and conceivably live to see completed. Suddenly, the stars are not a myth told to distant descendants. They are a destination a living person could reach for. But before you celebrate, understand the engineering nightmare hiding behind that single beautiful number. How do you stop a beam from spreading out across trillions of kilometers, losing all its power before it ever reaches the ship? How do you keep that same spacecraft from simply melting under the relentless heat of its own power source? And how do you aim a beam with pinpoint precision at a target racing away from you at a meaningful fraction of the speed of light? These are not laws of physics standing in our way. These are engineering problems. And engineering problems, however difficult, have a habit of eventually being solved. In 2016, an ambitious project set out to prove exactly this, a kilometer-wide ground-based laser array designed to launch a chip-sized probe toward another star entirely. The dream eventually ran out of something far more mundane than physics. Money. The project faded. But it left something behind that no failure could erase. Proof that this idea is no longer fantasy. It is simply waiting for the will and the money to finish what it started. Some engineers believe that, with enough investment, the same beaming technology could cut a trip to Mars down to just 45 days. 45 days. Not years. Not months. Weeks. Somewhere between a sail catching sunlight, an engine fed by lasers from home, and a problem still waiting for someone, somewhere, to fund it, the future of how humanity leaves this world is already being written. We just haven't decided yet how the story ends. 100 years ago, a single rocket rose 12 meters off a frozen field and fell back down. Today, we are designing engines that could ride a beam of light to another star. None of these machines are finished. None of them are perfect. Every single one carries a flaw, a danger, or a cost we have not fully solved. And yet, somehow, That has never once stopped us before. We are a species that once looked up at the birds and refused to accept that the sky belonged only to them. We looked at the edge of the atmosphere, where the air runs out and the body cannot survive, and we went there anyway. And now we are looking at a gap of trillions of kilometers and a weight of tens of thousands of years, and asking the same question we have always asked. Bet we could go there. Maybe we never truly solved the distance between worlds. Maybe we only ever learned to delay defeat by it a little longer, with fire, and then with light, and then with something we haven't even imagined yet. But somewhere out there, in a future none of us will live to see, someone may finally look back at Earth, not as the only home we have, but as the place we started from. The question was never really whether we could live. It was only ever how long we'd be willing to wait to find out. For one terrifying night, 7 human beings sat inside a tiny capsule, surrounded by the deadliest environment known to man. They survived. But not every mission in space gets a second chance. Some stories end in silence, some end in disaster. And one of those stories changed spaceflight forever. If you think this was terrifying, what happened next is even harder to believe.